We are going to look at the free radical halogenation reaction with an allylic substrate so that we can see resonance stabilization of a radical within its allylic. So when you do this, again, you're going to have a double bond in the alkene that you're dealing with. And you need to have a free radical generator on the arrow. There are several options that you could have. You could have bromine, chlorine, or NBS. Any of those are going to work fine. But the point is that you do have a free radical generator. I'm going to use NBS because in a previous mechanism I used bromine, and I just want to make sure that you are aware of how NBS actually works, which is N-bromosuccinimide. So you'd have NBS, and on the bottom of the arrow you would have heat or UV light. I'm going to use UV light as my free radical generator. So the way this mechanism actually works is you have to have an initiation step. If you're using bromine or chlorine, you would just break apart that covalent bond homolytically. With NBS, this is a 5-membered ring. It looks like this. And as you hit it with the UV light, the nitrogen-bromine bond is actually the one that breaks apart homolytically. Now I know that is not a completely covalent bond, but it breaks apart because one of the pieces that you generate has resonance stabilization of the radical. And I'm not going to draw all of its resonance structures. I did on the board in class. But this piece right here has that radical on that nitrogen being delocalized onto both of the oxygens. So there are 2 more resonance structures, which is why this is a favorable initiation step. There is resonance stabilization for the top component. The bromine atom at this point can then react with our alkene. So we're going to show how that actually occurs. Now, I hope you remember when you do free radical chemistry, in this manner, the radicals want to react with sp3 hybridized carbons. That has not changed in this case. So don't be doing anything with the carbons that are sp2 hybridized. But you still want to generate the most stable radical that you possibly can. So you're going to remove a hydrogen atom from the secondary carbon here in this case because you're going to be able to produce a resonance stabilized radical during the process here. So this bromine radical wants a hydrogen atom, just wants one hydrogen and its electron. So it's going to take it. The other electron is given to the carbon here. And that is going to produce a resonance stabilized radical here. And it has a resonance structure. And you have HBr. I'm just going to draw this here in a corner. But this is a propagation step. I should have put that on the other slide, but this is a propagation step because you have a radical and you produce a radical. And this particular radical, as we stated, has resonance stabilization of its radical. Typically, when these reactions are done, you want to generate a radical that the resonance structures are chemically equivalent structures. I haven't done that in this case to prove a point, but normally you would want to do this reaction in such a way that the 2 radicals are equivalent, the 2 resonance structures. In this case, the one there on the right is the predominant resonance structure. So at this point in time, this would react with another NBS molecule or the like to abstract the bromine from it. So I'm going to draw another NBS molecule since that's what we are using in this particular reaction. You could again be using Br2. There's nothing wrong with that. But the major product would be the one that comes from the major contributor to the resonance. So this one comes in and takes the bromine atom in this fashion. Or you could show the minor product, which would be from this minor resonance structure. Okay, same arrows pretty much. So the major product, we have the bromine on the tertiary carbon, and our minor product would have the bromine on the secondary carbon here. One of the problems with doing this reaction is that you tend to get a pretty good mix. So the red one may be a little bit more major, and the bottom one may be a little bit more minor, and this really isn't influenced by temperature. You always get kind of a mix. So I'm going to write that in big letters here. This is really a mix, which is why they like to make sure they have equivalent resonance structures, because you can't really say one's major and one's minor to any great extent by doing this. But you do produce these alkenyl halides.